So I think most of you know me by now. My name is John Foster. I was the chair of this conference. I'm a professor of petroleum and geosystems engineering at the University of Texas at Austin. As many of you know, this Congress has seen a great explosion in the number of talks related to data science and machine learning. And with that in mind, it's an especially great pleasure for me to introduce to you this morning one of the world's most famous data scientists, Dr. Travis Oliphant. Dr. Oliphant earned his BS and MS degrees in mathematics and electrical engineering from Brigham Young University, and later earned a PhD from the Mayo Clinic. From 2001 to 2007, he was a faculty member at BYU, and he directed the BYU Biomedical Imaging Lab, where he performed research on scanning impedance imaging. His publications from that time and subsequently have earned him over 10,000 citations, which is a respectable number in its own right, but speaks nothing to the impact he's had on scientific computing, data analysis, and machine learning. It was during that time that he began working on NumPy, which would become the fundamental data structures package in the Python computer language scientific software stack. I personally checked this morning. NumPy is a dependency for more than 285,000 source code repositories on GitHub. Keep in mind, those are the public repositories on GitHub. It has to be several multiples more in the software being worked on researchers' personal computers and stored in other cloud-based version control repositories. He was also one of the original contributors of the SciPy software suite that supplies most of the linear and nonlinear solvers, interpolation, quadrature routines, etc. to the scientific Python community. Again, as of this morning, SciPy is a dependency of more than 116,000 repositories on GitHub. Both NumPy and SciPy are a dependency of the world's most popular general-purpose machine learning framework, scikit-learn. Likewise, most of the popular deep learning frameworks, such as TensorFlow and PyTorch, use NumPy as a dependency and borrow heavily or exactly copy its API for tensor data structures. Around 2007, the bug of entrepreneurship and a vision to build communities that can enable scientific discovery through open source software overtook Dr. Oliphant, and he left academia, first serving as president of InThought, and then in 2012, he co-founded Continuum Analytics, which is now known as Anaconda. Anaconda distributes the world's most popular data science software platform with more than 16 million users and hundreds of enterprise customers. While at Continuum, he oversaw the creation of several new open source packages that enable big data exploration, speed up numerical computations in Python through just-in-time compilation, and out-of-core graph-directed big data computations. I'm talking about Bokeh, Numba, and Dask, respectively, and there are many others. I mentioned community building earlier. Dr. Oliphant also co-founded NumFocus, a nonprofit whose goal is to promote open practices in research, data, and scientific computing by serving as a fiscal sponsor for open source projects and organizing community-driven education programs. More than 30 open source projects in languages like Python, Julia, R, and others are currently supported by NumFocus. With his latest business venture, Quansight, he's trying to enable open source developers by building markets to create tools and incubate businesses from these products. He's only a year and a half in, and he's already on a faster growth trajectory than in the early days of Continuum. Did I mention he's not even 50 yet? I'm excited to introduce to you someone outside of our traditional community, but someone I know we can learn from, Dr. Travis Oliphant.
Wow, that's quite an introduction. I'm not sure who you're talking about. It's a pleasure to be here. It really is. I've been looking forward to this opportunity. My heart is still academics, even though I haven't been one for some time. I still feel at home with esteemed colleagues like you. He's actually given most of my talk, so this will be pretty quick. I've been doing a lot of things. I wanted to kind of connect and help people understand. I've been involved in academia for a while. My current passions really are around open source, math, science. Although on the math and science part, I like electromagnetism quite a bit. I know this is the mechanics conference, but I have some experience in fluid dynamics and especially ultrasound during my PhD. But that led me to entrepreneurship. And so over the past 12 years, I've spent a lot of time understanding how to connect the intellectual horsepower that's assembled in this room to the business world. One of my goals is essentially enable more of the influence of this room into the business markets. There's a lot of opportunity out there, actually, a lot of opportunity to help solve real problems with the intelligence that's here. So kind of the way I look at it is this is y'all, these thoroughbred horses, and I'm kind of the guy here just excited to kind of a little bit fish out of water, but excited to be here, excited to learn from you, and excited to maybe share a little bit about my experience that might help you. So I did start my career in computational science. Satellites measure backscatter over the ocean. This is in Earth climate studies. This is during a master's degree at BYU, where I first encountered science and math and kind of first fell in love with the opportunity to find information about the world by computational modeling and trying to invert that. These computer algorithms that I had a chance to be a part of would then estimate wind speed, vegetation, ice cover, and many more. It's fun work, actually. It got me realizing how much you could understand about the world by just careful observation, being careful about the measurements, being careful about the mathematics and the probability theory to understand what you really know. I left BYU to go to the Mayo Clinic, where I continued that enthusiasm for data, but this time for data about the body, and was inspired by people there who were trying to make medicine like science fiction, like the Star Trek of yesteryear. While I was there, I encountered a couple of problems. Elastography was the problem I ended up studying as a graduate student, and this was my sort of connection with mechanics. We were studying in a couple of ways. We were studying the motion, 400 hertz to 1,000 hertz, so not very high frequency motion, but put materials and then wiggle them, and then look at the wave patterns that would emerge. You can actually use MRI or ultrasound, higher frequency vibrations, and it would scatter off of the inhomogeneities in tissue. And then by that scattering, you could watch it move. You can keep track of that motion. Then if you could see all the motion, surely we could understand what's stiff and what's hard. We can invert that. So that was the problem that led me to Python in the first place. So I was fascinated by data. I was fascinated by physics. I was fascinated by trying to use that to solve interesting problems in the world. And then that led me to computer software. At Mayo Clinic is where I started the SciPy project, actually. And it's when I got kind of this bug of, oh, Python's this really powerful language that lets me write code at a high level, and I can still remember what I wrote when I come back to it. I had the interesting experience when I was a graduate student. I used some Perl to process data off of a tape drive on a VAX machine. And I wrote this Perl code to process, all the string processing that Perl had was really nice. And so I wrote this code, and it parsed all the data. Then I started to connect it to MATLAB. About a year later, I went back to that same Perl code, and I could not understand what I'd written. It was completely, I didn't understand it. It was when I first realized that this is kind of a write-once language. Now, there may be people in the audience who are actually better at Perl than I am, and for you, you've understood it and understand the beauty, and so it's not just write once. But for me, that was the experience. When I was in graduate school at the Mayo Clinic, I encountered Python. Had the very same kind of test drive. I wrote some code to process MRI data, and then went away, did some more stuff, did some parallel computing, did some ultrasound experiments, took some more classes. A year later, I came back, and the code made sense to me still. I understood it. And that's when I realized, hey, this is a language I might be able to actually make use of in my life. And so I continued to do that at Mayo Clinic. And then when I went to BYU, I was studying biomedical engineering, scanning impedance imaging, and by that time, everything I was doing was in Python. And I was just encouraging my students to use it. I was encouraging others to use it. It was still a pretty raw language. There weren't quite so many libraries as there are now. But you were just doing the work. So, SciPy was a collection of libraries to make Python more useful for scientific computing. They just kept growing over and over. And some of the students at BYU contributed to it. And it's just sort of the thing I kept doing more and more of. And effectively, the little side projects that I was involved with to do my research ended up becoming my life. It's a common story, actually. There's many others in that same similar circumstance. Actually, many of you out there probably have little side projects that are really cool. As I look out in the world and see all the open source software available, I realize it's exactly this. It's a lot of people doing interesting work, sharing that work with others, and by doing so, increasing the world. It's exactly the same as scientific study in the first place. It's sharing our work with each other so we can build on the shoulders of giants, and the whole, all of our knowledge can increase. So I ended up becoming more and more of a developer. And then the need to support the family ended up making me more of the pointy-haired guy. And sometimes I feel that way. I do still love to stay connected to technology. My favorite thing to do is mentor a lot of younger people to try to produce more. There's still a lot of ideas in your head, and many of you have this experience. You have ideas in your head, but you can't do them all at once, and so you try to rope in, nerd swipe, so to speak, as many people as you can to push your ideas forward. And that's kind of what I do today. It actually works if you can figure out how to direct capital that direction. And I'm still figuring that out entirely, but if you can figure out how to direct capital that direction, you get more and more done. It can exponentially grow. This is just a timeline that shows kind of a history. I've been at this a while, about 20 years. It's half my career, I hope. Maybe a third, probably only half. But a lot of things have changed. What's happened in the past 3 years, though, has shown me that things are accelerating. It's just getting more and more. There's a lot of people who have come to Python. If you look at 2015 and TensorFlow and PyTorch and all these machine learning languages, data science libraries, a lot of libraries have just come to the Python ecosystem. And it's a different place than it was 10 years ago. We were definitely pioneers 10, 15 years ago. Today, it's common, and there's a lot more happening. And it can be a lot to keep up. It takes a lot of work to keep up. The thing that's constantly driven me since I first fell in love with open source when I was a young graduate student is how do you sustain it? Because I understood market externalities. I didn't understand them perfectly, but I'd read some economic literature. I had 3 kids already when I was a graduate student, and I was giving my software away, and I thought, well, how is this going to work? I guess go get a job somewhere and keep working on open source, but why will they pay me to work on open source if I'm just giving it away? So I've been thinking about that a long time, and that kind of led to the entrepreneurship angle that's currently what I'm pursuing. Anaconda was a company started, was 40 years old when I started Anaconda. I thought you shouldn't start companies. I had this strange image in my head that only 20-somethings started companies because you could eat ramen noodles, you didn't have to make any money, and you could just sort of do something. And all the big company stories I heard in my head, that's how they started. Turns out that's not true. You can actually start a company at any age. Yes, there's capital requirements. Yes, it can be difficult. But if anybody's thinking about it out there, I'd love to talk to you about it. Love to give you some encouragement, help you kind of think through that. Happy to talk about it. Anaconda currently massively successful in getting users of the free stuff, and mildly successful in growing and getting people to pay for the stuff that keeps the lights on, which is the enterprise product. But really excited that the free stuff, the thing that I'm most excited about is a company that's sustainable is providing great value to millions, and that's an exciting thing for me. I think that was entirely the goal. At the same time, knowing that companies have their place, but so do foundations and so do organizations of nonprofits. So we organized a nonprofit so there was a home for open source software. NumPy.org, for example, the NumPy library. NumPy.org was owned by somebody named John Turner from Ornell, I believe, and he was just sitting on that domain. He happened to register it. Is he in the back there? Is John here? Oh, that is awesome. John, stand up, stand up. Do you mind? Thank you, thank you. I was actually really excited by this. I didn't expect that, but that's exciting because these libraries sort of evolve. People share some stuff, and they put out some code, and don't really think about what happens when somebody wants to claim the domain, or who's going to own the domain, or who should own it. Should I own the domain? Should a company own the domain? Who should own it? And so John reserved it so that the community could own it. And once there was an organization that was community-driven and community-governed, then he turned it over to that community, and that was the NumFocus. So it's very excited. NumFocus now is the project for NumPy, for Jupyter, for Pandas, and 30 and growing. The other thing we did with NumFocus, of course, to fund NumFocus, one of the ways we did it was by organizing the PyData conference series. There's 14 conferences this year, regional conferences happening all over the world. And it's not an expensive conference. It's actually very affordable. We ask people to donate the venue, and so any proceeds that come from that basically pay for half of the staff of NumFocus. So it helps keep that organization going. So very exciting to see that it can sustain, that organization can sustain itself, and that organization can then help a lot of other organizations grow. So over the years, this has been amazing to watch. When I first started using Python, it was a semi-obscure language. A lot of my colleagues in the electrical and computer engineering department weren't too thrilled that I was teaching everybody Python when they were teaching everybody MATLAB. And I couldn't only teach Python, I had to teach MATLAB too. But over the past 15 years, now all of a sudden Python's one of the most popular languages. It's overtaken in popularity all of these other languages. And the reason is machine learning. The reason is the enthusiasm that Google, Facebook, Microsoft, all these large companies have put in. And when they came saying, hey, we got these machine learning libraries, they weren't in Python, they were in C++, or in Torch, they're in these other languages, but they came and realized there's this massive community of millions of NumPy and SciPy users who kind of demanded that their libraries have Python bindings. And so that's what they did. And then that reinforced more growth. So Python keeps growing. It became very, very popular. It really astounded me. I think the existence of Anaconda helped too. I've had many people tell me that it was really hard for them to say, hey, start using Python, spend 3 days getting 300 libraries installed individually. And so with Anaconda, you could get them all with one download. There's a package manager, Conda, that manages them very, very, very easily all together, that's cross-platform, cross-language. So I think that helped. And then but what really helped is all the thousands and thousands of individual developers who spent nights, weekends, part of their day job, just making their corner of the world better, being a steward for the thing they care about. And that's created this amazing community of libraries and tools that is mind-blowing, really. It kind of illustrates planetary collaboration, which scientists understand, because you've been doing that for hundreds of years, actually. And as conferences like this, people come together and realize, yeah, we have something in common, we share, we publish papers. I see improvements to the way papers are being published, and I'm looking forward to more of those. But the whole point of science is to work and share our results for the betterment of the planet. And open source software has that same impact. And I see it as a sister or a cousin to the scientific method, the scientific community. I've been really, really thrilled and humbled. I did not expect this, actually. I did not expect it to be this popular. I knew it would be useful to a lot of people, but just how useful really still surprises me. Because there's lots, because I also know what's wrong with it. After being in the middle of code base for 20 years, you kind of realize, oh, that was a bad decision, that was a bad decision, we should have done this better, should have done this better. There's a lot of places that need to be improved. But it has had a huge impact, and as new scientific discoveries come out, it's thrilling. It's thrilling to meet these people when I get the chance to, and hear how they're taking the tools and doing something amazing with them. I was in Berlin in May. GitHub brought out the scientists, about 16, 17 of the scientists who had been a part of the black hole imaging experiment, the HT experiment, and they came out, did a beautiful job of explaining exactly what they did. It was very impressive to understand how they built a radio telescope that was basically the size of the Earth, because they used the rotation of the Earth to take measurements from a tiny point in the sky over a period of many, many days. And it was petabytes of data that they then processed to get megabytes of signal. There was a lot of processing done in order to get that signal, and they had to do it 4 different ways just to make sure they believed what they were getting. They weren't just fixating on noise. And so it's very interesting to see that collaboration that occurred, and how the software helped that interplanetary collaboration to accomplish something very interesting. So I'm going to go pretty quickly through a number of these tools, mostly to kind of, for those who may not be familiar with them, to be aware of some things, and maybe some things you're not aware of, learn a little bit. You already understand NumPy. You've heard about it. NumPy is an array object. It allows, really it's fairly straightforward. It's a simple array object that has slicing and shaping of particular data types, and it's got fast math. You can think of an array, and you can slice that array and do computations with that array. It's got some interesting slicing syntax. SciPy was actually my first project. Many people don't really recognize that, but I was a grad student when I first started putting software on the web. This was our Facebook, back before we had Facebook. Graduate students would just share code with each other, and then we kind of geek out over each other's code. We wouldn't post tweets or Facebook updates. We'd post code updates to the web. And it was the first time you could see that, hey, the web was kind of a social activity. Some of us probably could have figured out Facebook if we were thinking that way, but we didn't. We just thought about sharing code. But it was very, very enjoyable. And actually, this is what kind of got me addicted, is actually the community aspect of software. I think it's similar to some of you. Science is addicting because of the people you meet, the problems you solve. And those epiphanies that occur together, those shared epiphanies, are really powerful bonding mechanisms, bonding experiences. And this is what happened with SciPy for me. It got me addicted. SciPy is a collection of libraries. Basically, it was, oh, I need to do simulation. I need to simulate MRI. I need an ordinary differential equation solver. Oh, I need integration. Oh, hey, there's some Fortran code out there that's been there since the 70s. Still good. I just need to link it into Python. So a lot of the work I did was actually reusing old software and making it new, making it more accessible. Definitely myself did not write all of this capability. A lot of it was just reusing other things and being a bridge, building a bridge. Then what happened is you start to work, a lot of people start to join you and they have their own ideas and they do it. At first, SciPy had a plotting system, but pretty soon John Hunter said, oh, that plotting system you had stinks, and it did. And he wrote something else called Matplotlib that has become very, very popular, used by a lot of libraries. It's a powerful plotting engine, lets you plot things quickly and easily. Images, histograms, even XKCD comics. They've got a style for XKCD that's kind of fun if you learn how to use it. And then what really helped data science take off was Wes McKinney's Pandas. Pandas is it's basically database and Excel in Python. So anything you do in Excel, anything you do with the database, you can do with Pandas commands. So group bys and aggregations and data munging and processing. There's basically a version of this at every hedge fund in 2011. Every hedge fund, every prop trading firm, every investment bank had a version of this that they had written. And AQR, Wes got AQR to release theirs. It's kind of a lesson about, if you don't open source what you're working on, somebody else will open source a worse version. And Pandas is great, but other people, I've heard this, oh man, mine was better, and now I have to port to Pandas. That'll happen if you don't open source your stuff. The community will take off with something else. So Pandas is very useful. The thing that's made Python take off for the last 3 years, though, is the machine learning part. Scikit-learn, SciPy, when it first came out, contemplated being this collection of all this capability, including machine learning. Very quickly, we realized that, wait, this is too big. You can't actually have 10,000 people collaborate on a single project. There's sort of, I think, fundamental limits of human cooperation. You can have people gather and talk, but you can't work on a library together. Certainly just shipping it to people and understanding those APIs, those scales. So scikits emerged as basically people took off little segments of the space and said, we'll call them scikits, and scikit-learn was one of the most popular. Scikit-image is another one. But scikit-learn was started as a summer of code student who just got it started, then picked up by INRIA, and a bunch of people all over the world. Over 1,000 contributors have made scikit-learn into really the standard, the de facto API for machine learning. It's got a really beautiful API. It's got a really beautiful tutorial. If you want to understand machine learning, if you want to have a student who wants to understand machine learning, just point them to the scikit-learn documentation, and they're going to be on their way pretty quickly. And a lot of other libraries follow the same documentation. So it's a very, very nice just resource now. So basic, you can load data. There's some data there, and all the data has a common format. It's a common array with a certain structure. Then you can choose a model or build a pipeline of models. Once you have that, you have to build that model and parameterize that model. You have the meta parameters for the model, the hyperparameters. There's a lot of choices. Once you have the model, in this case that CLF object, then you call fit on the data. If it's supervised and you have labels that you know, make sure you're reserving some of the data for testing. So you just fit all the training data, so you have some for testing, otherwise you won't know what you did. That's the cross-validation capability. And then to figure out new values, you predict. So that's kind of the API. You could imagine doing this API with a model you build from computation, actually. It really is quite arbitrary what that model is. This is just a fairly straightforward API. And then cross-validating it on the training data, the test data, tells people how you did. So that's scikit-learn, very, very popular library, very easy to use library. And then what's really helped the message of these libraries take off is the Jupyter Notebook. The Jupyter Notebook emerged from a few friends of mine in 2012, and it first was called IPython. And the notebook is not a new idea. It's been around for decades in various forms or another, but it basically combines text. It combines text with code, with output, and allows you just to have all that together. It's a really great place to experiment. It's like a lab notebook. And you can write things, they're self-contained, you can share them with other people, they have code that can run. In fact, a lot of people, right now there's kind of a little bit of a tug-of-war going on where some people are like, no, notebooks are everything and that's all I do is code in the notebook. And others are like, wait a minute, you gotta have a script there somewhere. Like, surely you've gotta factor some of your code into a library. And if you're at all a developer, you want to make libraries. If you're just a data scientist, you're just a lab worker, you kind of don't want to build libraries. You just want to be notebooks all the way down. So that's an emerging activity. We'll see what happens. I think there's a few trends that are happening in that direction, but they're a great tool. And you can, just an example of the kind of tables and plots and code and text that you can mix together and send to people. Jupyter Lab, the first version of Jupyter was great, but it's hard to extend. It's hard for the developers to make it better, and it was just the notebook. Jupyter Lab is a project that's just reached 1.0. It's an extensible application builder, basically. It's more than notebooks. It's got terminals, plugins of various kinds, map plugins, image plugins, browser plugins. This is all in the browser, all in the web browser. It's the future of Jupyter Project. It's actually an extensible data-centric app building tool for the web. And as you understand that, you can actually, there's a lot of opportunity to basically replace a whole lot of applications with plugins to Jupyter Lab. It's not very difficult to connect things through the web through a Jupyter Lab plugin to data, to machine learning libraries. I'm looking forward to what people are going to do with this over the next 2, 3, 4, 5 years. Jupyter Lab makes it easy to go from notebooks. I'm working on some code in a notebook, working on experiments in the notebook, to applications. Let's say dashboards are maybe in the middle there. Just to quick dashboards that I then send to people as a link, and they can bring it up and interact with it. How do they do that? They do that with web visualization libraries. They can do that with Matplotlib, but there's other web visualization libraries that have emerged, things like Bokeh, things like Plotly, things like Altair that sit on top of D3. Bokeh just makes it very easy to build interactive plots as a Python programmer. Without knowing JavaScript, you write Python, and it plops up a very nice interactive viewer on in the browser that you can experiment with, explore with the data. A lot of examples of all kinds of plots you can experiment with. There's tools written on top of Bokeh. Bokeh's probably medium level. It's not super high level, but it's medium level. It's not really low level either. It's medium. And there's tools like Chartify that sit on top. Oops, I think I'm going to break my connection. Sorry about that. We're back. Then there's tools like, as you and many of here in this audience are going to have lots of data. You're simulating data. You're going to generate a lot of it. Well, how do you visualize a lot of data? That's a hard problem. There's actually a couple of really nice sets of tools these days. Data Shader, VAX is another, that help you actually set up a rendering pipeline behind the scenes so it's seamless to you. You don't have to think much about it. You suddenly have billions of points, and then it shows you a rendering of that as you zoom in, it re-renders. And that can be done at interactive speeds with some of the capabilities that are now available in the Python ecosystem. So this is an exciting data shader. Look it up if you haven't heard of it. Most recently, just this summer, a tool called Panel was released. Panel has been being worked on for several years, but it allows you to make dashboards and little mini apps very, very quickly in the web. So for many people, Panel is exactly what you're looking for. It's a tool that lets you play with widgets, lets you build them really quickly in Python code only, you don't have to know JavaScript, and then you can just release, and it sits on top of any plotting library. This is an example of the Gapminder demo showing the improvement of the quality of life all over the world, but in Bokeh, Altair, Plotly, and Matplotlib. Panel can wrap all of them. Another example showing integration with map view data. Very easy, relatively easy, much easier than it would be otherwise, and you can stay in Python and do it. So check it out, panel.pyviz.org. Finally, I'm going to talk about a couple of the libraries we spoke of before I get to a final topic I want to cover about how do we contribute more to these communities? How do we ourselves start to build on top of these tools that are already there? Numba, if you haven't heard of Numba and you're using Python, you're missing out. So go right now and learn about it, because it's pretty easy to learn about. It's just you can take Python code and actually put a decorator around it, and it can be as fast as C. Right? So I'll say that again. You can write Python syntax, and it can be as fast as C. I know there's people in the room going, no, it's got to be Fortran, got to be C. It doesn't, actually. C, Fortran are just ASCII, and they use a back-end code generator. Many of they're Clang and FLang, back-end code generators. Numba does the same thing. It takes Python code, a subset of Python code, to be clear, a subset of numerical styled Python code, and translate that to machine code. What that allows you to do is interactively generate high-performing code. Maybe it's a plugin, maybe it's a callback to a larger system you can that you can interactively engage with. This can make it a lot easier to integrate with databases or large code bases where you need to sort of generate little code snippets. Now you can, and they can be machine code speeds. Very excited by this tool. This is something I'd wanted for a long time. It only took us about 4 years to write it. And Intel and NVIDIA and AMD have all contributed to it at this point. So very excited about Numba. Although, as you're thinking about speed, this is from Stan Siebert's talk on Numba at SciPy just recently, and I loved it. His Maslow's hierarchy of software project needs. Definitely, as you think about your software projects, this is something you should pay attention to. Because is it fast enough is the sort of the final one, and most of us are actually denying the other needs our software projects have. Like, is there documentation? Are there tests? Does it work? Is it easy to install? As I was perusing some of the simulation tools around that can do computational mechanics, I noticed some of them. There looks like there's a lot of great code there, but not necessarily documented or easy to install or really helpful to help people get going with it. So there may be some opportunity there to bring more people in. The one thing that was very clear is you get more users if you have documentation and install instructions. Not too surprising, perhaps, but that's sort of a lot of time was spent. Sometimes I wonder, how did I end up writing a package manager when I started doing MRI research? It was a funny journey, right? Basically to try to help people get the stuff installed. It turned out it was a packaging problem. The next library we spend time on that's also really powerful for integrating with your computational loads and it can help you use Python at scale is Dask. So many people are familiar with the Hadoop world. A lot of money spent in the Hadoop world. Less money spent here, but a better tool emerged, in my mind, in my opinion, because it integrates cleanly with Python. It rests simply with Python. If you're using Java, if you're using Scala, and that's all you're using, great. The Hadoop world, the Spark world works really well. But if Python's your source, you're using native code, Fortran, that's where you're living, then the Java scalable solutions don't really fit with your code generation, with your code. The JVM and native code have always had a little bit of a challenge relationship. And so, integrating those two can be difficult. Dask makes it really simple. Dask lets you scale your Python code to thousands of nodes or run it on your laptop with multi-core. So it sits on top of NumPy or Pandas, gives you a logical array that's as large as your memory or your node farm, or a data frame that's as large as your memory or the memory in all your nodes. And then their Dask ML is starting to sit on top of scikit-learn. So it's basically scaling the SciPy community. You can scale up to clusters or use it on your laptop. It's got really nice visualizations, actually. A lot of people use Dask. They keep using it because it mesmerizes them with its visualizations. I've heard, I was just in Chicago talking to somebody who loves Dask, and that's why. So it helps you understand your parallelism because it shows you what's running. There's a scheduler, there's a visualization written in Bokeh for the scheduler that shows you what's working and how it's working. Now, deep learning frameworks have changed the game for the Python community, and it's still emerging what this is going to imply. There's still a bit of, let's call it churn. There's still there's a lot of new libraries. They're still kind of competing to see how they're going to play out. Theano was the very first, so I talk about it here. Even though it's not used as heavily, it was the very first. Theano gave rise to several other deep learning libraries. Now I'll put these four. There are others up there, there's others out there, but these are the ones I think are worth paying attention to and looking at and evaluating for yourself. TensorFlow, PyTorch, MXNet, Chainer. TensorFlow is from Google, PyTorch is from Facebook, MXNet is from Amazon. Chainer is from Preferred Networks, which is a scrappy consulting company that works for Toyota. Toyota has some investment in them. They built a machine learning framework on top of NumPy and SciPy, which is what anybody who started in the Python world would have done, because NumPy and SciPy already had most of the elements of a machine learning framework. They just lacked a couple of things. They lacked the ability to take derivatives easily. Kind of automatic differentiation wasn't simple. So they added AutoGrad. Chainer folks added AutoGrad. It also lacked the ability to compute on GPUs. And so the Chainer folks added CuPy. And so with those two features, they could replicate all of the other things needed for deep learning code, and they have it. Chainer works very well. It's the second most popular tool in Japan. All the documentation's in English, but the developers are all in Japan. So I tend to point people to Chainer and PyTorch. I like the PyTorch community. I like Chainer because it's easier to use and easier to integrate with the Python with what you have already. You're not sort of installing a whole new ND array. So the result is there's many competing similar choices for deep learning right now. And some of you in the audience may have a different recommendation, and that's okay. That's what's happening. There are a lot of opportunities to use these libraries. As I looked around, this is the paper that caught my attention that might be of interest to some of you. Many of you have probably already read it. I would definitely recommend it. It goes into quite a bit of detail about all the different ways you can apply deep learning to computational mechanics. This came out in Frontiers Materials in May. And it was actually pretty impressive and on point as to the kinds of things you can use deep learning, which at its core is curve fitting, high-dimensional curve fitting, nonlinear curve fitting, with when you have lots of data, and then you have regularization methods that are ensuring your gradients aren't going to zero, so you stop learning. There's different techniques they've done in order to have more and more layers so that the numerical properties work. That's kind of the big deal that's happened is the computational ability, and the amount of large data has been the mother of invention to improve the numerical approaches being taken. And the reason that's happened is because the tools have enabled them to iterate more quickly. The key to progress is iteration. Speaking of speed and iteration, GPUs are coming into their own. They're almost to the point, let's say another year, maybe a year and a half, and you're going to have most of the functionality of NumPy, SciPy, scikit-learn available that works on GPUs. And it'll be basically a pretty straightforward mechanism to use your GPUs. NVIDIA is pushing hard on this. At the same time, Intel will come out with new hardware that'll also have these capabilities. So it's an exciting time, actually, to be alive and to be using this. I'm going to skip ahead. I have a few things here on community, but I'm going to skip ahead just to the final kind of recommendations and thoughts I have about how do you sit on top of this, take what you have, and do more with it. I think the key is to recognize that all these projects, I've had an opportunity to be a part of a lot of projects, they don't all emerge from a group. You don't take a room of 10 people or 100 or 1,000 people and suddenly projects emerge. It always takes a small group to actually get something off the ground. You have to have a small enough group you can all talk to each other without taking 10 weeks to do it. However, that small group has to grow beyond the small group to get more effort. So that group has to grow. So I take Khan as an example. It started with one person, and now there's 1,200 contributors to Conda Forge, building 7,000 packages pretty much every day in a CI/CD system. To do this, it actually does take some humanity. It's a little bit, what are the principles of humanity we have to follow? Actually, Cinderella had it right. Have courage and be kind. It's a pretty good statement of what do you do to respect each other, respect people, think deeply about how we talk and act towards each other, and work together. I'm going to skip these quickly, but there's a couple of really good thoughts about how do you build communities together. Across the world, these principles have emerged, and they're still the same. And I'll finally end with, there's a couple of things comments I want to make towards the end. The changes are going to keep accelerating. We've seen massive growth in software, massive growth in hardware. This isn't going to slow down anytime soon. Hardware is going to be improving and diversifying. In some sense, the world we're in, array computing, doing computing at scale for physics, was kind of a lonely place as we started in Fortran and everybody was like, yeah, we're all doing this to do science. Then the business world took off and objects and data processing became all the rage and GUIs and kind of left alone the science. Well, now it's back with a vengeance as deep learning is closer. It's a lot closer to the kind of computations we're doing. That's what all of a sudden a lot of people are buying. And so that means that we're gonna have more hardware that we're gonna have to figure out what to do with. And it won't be tailored to won't be tailored to this group's problems. It'll be tailored to slightly different problems, but very close. And if people that can figure out how to use that and apply it to the problems you have and iterate quickly are going to I think there'll be a lot of success coming out of that. So interconnects are improving, data movement's going to be improving. So you have this combination of data will be going into one place, so you can take advantage of high interconnects in the supercomputers. You're going to come back to the mainframe. But at the same time, you'll have smaller edge devices as well. So it's kind of a question of what will happen to the laptops and desktops. I think we'll have edges. Maybe they'll all be the same. We'll just have many more of these. And there'll be more and more libraries to integrate with. So what do you do? Share knowledge. I think it's actually more important than publishing papers behind paywalls. Probably the most controversial thing I'll say in this conference. But I definitely believe that. I think it's past time that we sort of tolerate that kind of activity in our scientific ecosystems, and there's ways to fix it. It's not easy. I understand inertia. Make infrastructure code and libraries open source. I'm actually not a fan of the GPL. I know many people do it here, and the reason is because GPL makes it harder to do more with it. There are some things like polished user interfaces, like cloud services, that can be proprietary, that actually can help drive money into the open source ecosystem. And the GPL just basically prevents all of that. I know that's controversial as well. Happy if you disagree with me, we can talk about that. If you build a company, just remember that all the stuff that goes around to selling that thing is actually a lot. And sometimes we lose sight of that. Managing, maintaining, selling, supporting the ideas, it's more than you think typically. Use higher level languages. Dask, Numba are making it possible to use high-level languages at the same speed as C. And that's pretty transformative. Build communities around your public efforts. Make a difference today. Dive in vigorously. There's some young people in the audience and some younger people in the audience, still young people in the audience. You can always do something. Contribute to something you're passionate about. Step back. Think about what's really important. Think about what's missing. That's when some of us still young people can typically do is we understand kind of a lot of things that have been happening. We can understand what's still missing and encourage other people and encourage ourselves to push it. Look for what others have done and build and use their work. That's how we make progress faster. And then teach others what to do. Break things into chunks and iterate quickly. Don't be afraid to fail. There's definitely failures. I didn't talk about them, but I'm happy to go into detail with anybody that wants to know about the failures that have happened along the way. So that's what I want to talk about. I hope you got something out of that. I'm happy to spend time. I'll be here for a little while. If others want to come up and chat, I'm happy to answer questions and talk a little bit later. Thanks for having me here. It's been a pleasure.
So we do have time for some questions. I know there are a lot of you taking pictures of the slides. I guess I should have mentioned this at the beginning of the Congress, but all the plenary talks and semi-plenary talks have been recorded and will be available on the USACM YouTube page at some point after we can process them a little bit. So anyway, with that, if there's any questions for Travis now, we can field a few questions, and I know he'll probably stick around and talk to as many people as that are willing to come up and talk to him. So is there any questions? Armando.
Great talk, thank you. You mentioned that you don't like a GPL license. Which one do you recommend and why?
A variety, BSD, MIT, anything that just allows people to use the code. I understand the reasons for the GPL, and I respect that. I mean, LGPL can actually work and honor some of those reasons, but still allow you to build on top of it. I firmly believe that most software will be open source, but there still will be some things that aren't. And there's a reason for that, and it's okay. So that's why. So, any other questions?
Okay, well, if not, we'll thank Travis one more time.
Awesome, thank you.